Yep.
Okay, so I'm in the midst of organizing and putting things together for my whatchamacallit seminar coming up. But for this week, I will be talking about this paper. It was actually a pretty big review paper that looked at the stratospheric influences on tropospheric jet streams, storm tracks, and weather. Okay, so
Quick
starting
question, next week you're
yes.
going to come to us with the
Yes.
presentation you're giving to the.
Next week is my practice seminar, and then the Monday after will be my seminar at 3:30. Before the drop.
10.
I got your invite.
You got it?
Mhm.
Okay, cool.
Me too. Yep.
Okay,
Sorry about that.
no, you're good. All right, so starting with tropospheric response to stratosphere-troposphere coupling in a very general sense. So the leading mode of variability in the stratosphere is the variation in the strength of the stratospheric polar vortex rather than its latitude. And it's also the strength in the polar vortex rather than the latitude that is believed to be more important for troposphere stratosphere coupling, which I will be talking about in the next slide. But anyways, the tropospheric jet is generally displaced equatorward when the SPV or stratospheric polar vortex is weakened and displaced polwards when the SPV is strengthened. Now, when I say the tropospheric jet, in this paper itself, they didn't really specify too well which, because in the troposphere we have the thermally driven jet based off of latent heating in the tropics and the Hadley circulation, and then we have the eddy-driven jet. Now, from other papers, from what I understand, this is more referring to the eddy-driven jet. Anyway, so it's displaced equatorward when the polar vortex is weakened and displaced polwards when the SPV is strengthened. Now, the proposed mechanism in this paper is visualized through the transformed Eulerian mean momentum equation. Okay, now bear with me on this.
Sorry, Henrik, just
Yeah.
quick, what does the first sentence mean rather than the latitude? What does it mean?
I think the second part, what I was saying was that.
No, first one, blue one.
Yeah, the second part of that first sentence. You're referring to the
yeah.
dynamical coupling between the troposphere and the
Just
stratosphere, right?
wondering what does it mean rather than latitude?
The leading mode of variability, variation rather than its latitude. Not completely sure, but that was why I brought up that second part, which was saying to understand the dynamical coupling between the troposphere and the stratosphere, it is the speed of the polar vortex which matters much more than the latitude, which comes to the transformed Eulerian mean momentum equation, which I'm going to talk about in the next slide.
Maybe, okay.
Yeah. Okay, so from this paper, they proposed a way of visualizing the effects of wave forcing and the speed of the zonal mean westerly winds. So starting with this equation over here, U bar refers to our zonal mean of our westerly winds. V bar star, which is, where'd you go? V bar star and W bar star are the northward and upward components of the residual mean circulation, where terms 1 and terms 2 represent the mean westerly momentum transported across the latitudes for this first term over here, and in the vertical, the second term over here. Now this circulation, the residual mean circulation, roughly determines the transport of mass throughout the stratosphere. Okay, for the third term, the transport of angular momentum by waves is represented by the wave activity flux, F, over here. With term 3, the whole of term 3 representing the wave activity flux convergence, and then X bar represents the small scale gravity waves, which also act as wave forcing that could affect the polar vortex. And then the other terms are just minor terms like T equals time, Z is latitude, Z is altitude, phi is latitude, rho naught is the mean atmospheric density at altitude Z, A is radius of the Earth, and the subscripts denote the derivative with respect to that variable. So like here and here. So variability in the speed of the polar vortex is forced by waves propagating up from the troposphere, going like this, which is represented by terms 3 and terms 4. It's specifically the convergence of this wave activity flux in the stratosphere, which has an effect on the speed of the polar vortex. So these waves transport momentum upward, where if not reflected back downward or refracted either towards the polar regions or the tropics, they break in the stratosphere, depositing energy and angular momentum through the wave flux convergence, or term 3. And then this induces a change to the residual mean mass circulation, as represented by the V bar star and the W bar star. Okay, and then this circulation makes it so that the mean westerly momentum transported by terms 1 and 2 acts to conserve angular momentum and mass continuity. And then these two effects being the terms 3 and 4 and terms 1 and 2, they oppose each other, so that if the wave breaking, term 3, if it decreases, then the polar vortex will speed up, accompanied by a equatorward momentum transport. And then by mass continuity, upward transport, adiabatic cooling, as represented by this blue color over here, increase of the tropopause height, and lowering of sea level pressures are induced over the polar cap, with sinking adiabatic warming, as represented by this red shading and the red arrow, a decrease of the tropopause height, and higher sea level pressures in the lower latitudes, which, two reasons that I don't really understand, leads to a northward shift of this tropospheric jet.
Hey, Henrik.
Yeah.
Okay, so in layman's terms, okay, I don't know what's going on.
I
So,
don't.
so is this one equation's trying to explain what now? Like, and multiple processes?
Yes.
That affect what?
This one equation is trying to explain the wave forcing component of the dynamical coupling between the troposphere and the stratosphere in terms of the change of the speed of the stratospheric polar jets.
But what,
Are you sure?
what's the?
According to this paper,
So,
yeah.
okay,
I'm not sure,
So
but
the
this
U
paper
bar
thinks that.
T, or the U bar T is what is this now?
This is your
stratospheric,
yeah. This is stratospheric
and it's a function
zonally
of
averaged winds.
It's a function. Okay, so what, one or?
Okay. It's
or
a
is it-
function of our. This is our meridional residual mean circulation.
Okay, wait, hold on. So, okay, so.
There is no layman's
No, no,
terms
yeah, I
for
know.
this.
But so all these numbers
Maybe I
on
should've
this.
skipped this.
No. All these numbers on this plot are referring to what now? Like, is it referring to this equation or?
No. These
These are like
aren't referring to the equations.
Steps, right?
No, these are huh?
These are like the steps, the numbers.
Yes, they're supposed to be the steps.
Okay, so
Even
one being
wait.
the.
Wait, actually, the steps. No, that doesn't make sense. I was kind of having trouble understanding that too.
Okay,
but
so if you're having trouble understanding that, I'm really having trouble understanding that. But so okay.
yeah, this is 4, even though this is the wave activity.
But point
forcing.
being is.
But there should be a figure absence on that figure.
There wasn't, no.
There wasn't?
Yeah, that's
Oh.
always.
Okay, so
It's
point
difficult,
being
yeah.
is that the tropospheric jet is
There's constantly wave forcing.
from the surface
Yes, from the surface of
Vertical
the troposphere.
wave?
Yes, there's vertical wave forcing
that penetrates into the stratosphere.
that either penetrates,
Or
gets
gets
reflected, or refracted, and that depends on this equation that I don't understand. But anyway, so the portion of it that gets absorbed into the stratosphere, it breaks in the stratosphere and it deposits its angular momentum. Now, when that wave forcing is weaker, then the forcing that weakens the polar vortex is smaller. And then that perturbation itself induces a change in this residual mean circulation based off of keeping momentum conserved and mass continuity.
So
So
this is just a troposphere. This is showing only effect on the stratosphere from a troposphere change.
This is showing effect on the stratosphere, and then back to the troposphere.
So
I don't
some-
see the downward coupling though, I guess.
Is it two?
It's
Well, but even two is I mean, it stops at the tropopause. It doesn't show a mechanism or any dynamics in how it would impact the troposphere, right? I mean, the height of the tropopause has changed, but
I mean, this arrow supposedly goes all the way down. That's
arrow,
what
what is that
I
arrow?
don't think
though?
so.
Yeah.
Yeah, it doesn't show it here, but it says it right here in my notes, which is directly from the explanation on this thing.
So you're reading us the paper.
I was trying to.
I'm
So
really
that diagram.
It's not the
It's
greatest
a good diagram, I imagine, but it needs a lot of
Since-
work.
I did not like this diagram, but I
Anyways,
was trying to explain
just
it.
a general comment. I think you are almost at the end of your research. You are writing the thesis. So can you add anything from this paper that you are reading right now?
Can I add anything from
Yeah,
this paper
right.
specifically?
Yeah. for like-
Just some general notes from it, not
Right.
specifically from this
right.
diagram.
Mo- I mean, like looking at this figure, explaining the detail of that equation. Can you add any component in your research so that your research can be?
I mean, the fact that this paper was trying to explain why a strengthening of
Right.
the polar vortex leads to
Right.
a northern shift of the jet stream,
I see.
and that's usually accompanied by a positive NAM signal.
I see.
Yeah,
Yeah.
and
Be-
some other
be-
stuff.
be- because
do, you
I,
do you believe it?
Do
Do you believe it?
I believe it?
Yeah.
I mean, there's. I don't know if I believe it, but it's. I think the mechanism they were providing when I was reading the paper seemed pretty sound.
So
it
this is
seems
a
like it
review.
makes sense.
Yeah, it mostly makes
This is
sense.
a review paper, right?
This is a review
So
paper.
this plot's probably combining many,
Yeah,
I
exactly.
assume many
Right.
papers.
Many
on-
papers, yeah.
So I'm wondering, like, so there's like 3 threes here, and I don't know, maybe that's like connecting.
Yeah, there really wasn't too many
so
notes.
these
on
are
explaining
the.
numbers.
I think
It's just
those numbers are
confusing.
kind of related to the other papers, for example.
Maybe, yeah, it might.
No, it wasn't.
Not exactly, but the mechanism they are describing in different ways. So they are trying to put everything together so that it makes sense.
Okay, but so
Maybe.
point is, Henrik, you need to learn, okay, later.
Huh?
You need to learn what the equation means based on the Horton.
Yeah.
It's the same
Okay.
equation Horton show it. Okay?
Yeah,
So
that-
you need to learn, okay? What does it mean?
Yeah. So
What can I do with this?
What can you do with this?
Yeah. What can a
Uh,
climate scientist do with this?
You could use the different components, I suppose, to test how maybe the tropospheric jet might vacillate whether north or south depending on those different terms. Like if the wave.
And why would I want to do that?
Why would you want to do that? I don't know, 'cause it's fun.
So it's just quick comment, okay?
Okay.
So this is a tendency term, I believe, right?
Yeah, because
small
it's
t is a test, so
derivative
d
with
dt.
respect to time. Yeah.
So usually
Yeah,
we want to
dt.
see how jet core, the stratospheric jet core produced. And
Right.
then easy way is first just zonal mean. So you don't need to think about zonal difference, just on zonal mean. So in Henrik say bar mean zonal mean, right?
Mm.
And then the people want to say how jet stream changing with time. What is the forcing? And then roughly 3 forcing, 1, 2, 3, 4. And maybe this is usually DGCS, but this is kind of meridional circulation. So in the stratosphere, troposphere, define the meridional circulation.
So the way I see it is, at least, I mean, if it's a review paper regarding the interaction, that some of these processes in this equation
Yep.
must come from the troposphere.
Yes.
It's so I think that this guy too might be more like a stratosphere circulation changes. Okay, in the stratosphere usually have a bigger change. Troposphere is more. Troposphere we have a Hadley circulation, Ferrier circulation, polar circulation, right? The
Right.
stratosphere usually meridional circulation only have one circulation.
But it seems like the forcing, there's according to Henrik, there's some vertical wave flux.
Yes.
Vertical wave flux is this one, so it's coming from the eddy activity. in
And
the
these
troposphere.
two, they induce these two. It's these two that are balanced with these two
Well,
through momentum transport.
Well, if we assume the tendency number is 0, okay?
Okay.
So this is just equation, and the C, 3 component, 1 to C. One, this is a wave activity flux. So wave coming from the troposphere and that will go to the stratosphere, and usually, as Henrik said, it's something like a reflection instability or something, but something stuff, reflection or something. But basically, energy go to the top of the stratosphere or mesosphere, and then that energy have a wave break, and then with the wind change, it's just propagating.
So,
down.
so for me, the only connection here I see is that wave activity flux,
That
at
one.
least from the troposphere to the stratosphere.
Yeah, but there is some like a connection maybe in here. We don't know how
Sure.
do they say that. I don't know. Basically, stratosphere and the troposphere separating, and there's some like a there's just different force.
Yeah,
that
yeah,
one may be
yeah.
coming from stuff. So, but basically, roughly speaking,
This is the equation in Holton?
mm-hmm,
Oh, I don't know. I don't remember which equation.
I
This
think you can
chapter 10.
zonal
Oh.
average Elias and Palmer
Yeah,
equation
part
or
of that.
something. Yeah, something you can see with the
Okay.
general one. Okay, but as you say, troposphere to stratosphere impact basically coming from wave activity flux, energy propagation. Also be wave energy propagation.
Right.
The vertical one. That one is the main part.
But then the idea was, and how that feeds back to the troposphere was through the residual mean circulation, where what was it?
Well, so
When
for me, whatever that green 5 seems to be
This is-
partly in the troposphere, partly in the.
Yeah,
This is
so,
our tropospheric jet,
So one idea is
Oh, that is
jet
the
stream.
jet.
So
and this isn't
stratospheric
referring
jet
to the
stream,
shift of the
so
jet.
in this topos, wave activity first go to the top, and then it's changed to the acceleration of the zonal wind, and that change is gradually degrade, propagate to the downward.
How long does that take?
Maybe.
Well-
How long does it take? It's usually 1 to 3 months from the top
Oh,
to the
wow.
bottom. This is more faster, within the 1 month. Go there, and then this propagation is more slower. And then maybe some part is coming to the troposphere. That one is a suggestion, or some studies suggest that one.
Wait, so is 5 the mid-latitude jet? I mean, that thing in the troposphere that's to the left of the green one, the red one, that one,
This one?
yeah. Is that just the jet?
This is
I don't
supposed
know.
to. This is supposed to be
I
the.
don't know that one.
They did not define these terms at all.
I don't know
but,
what it is.
It's supposed to be the jet.
I don't
So
know
for
why
me,
I don't know
for
why
me, it
this
looks like
like-
5.
This is the shift of the surface cyclones. This was the last part
I know
that
what
comes
to
to the
say, but
tropospheric
I know
eddy
I
feedbacks.
don't know how does it relate to how do they connect all of them. Okay.
Through the residual mean circulation, which was these two terms over here.
No. Hey. So, so in that case, what you think in this guy, U-bar? You think U-bar is vertical,
No.
only depend on the Z, or only depend on the X, or this guy reflecting the zonal and vertical, or this guy only reflects the stratosphere?
That's even
I mean, it
Right.
reflects all of these terms.
Well, I'm asking what coordinate is this guy?
What coordinate?
Yeah, because these are zonal mean, so there's no X dimension.
Okay, yeah.
Well, what
So with
dimension
the
is it?
y and z dimension.
So it's to say Y and the Z dimension. Y and Z dimension using this one, right?
I think so, yeah, because it's.
So this is
zonally
more
stuff.
reflective of middle latitude jet stream equation. Okay. Tropical region equations, I think, slightly different. So need to check, and then usually we use this equation to show stratospheric jet stream activity. But you need to
Okay.
check this is reflective of vertical information or not. You know what I'm saying?
I think so, yeah.
Okay. So if you understand that one more better, what coordinates they are talking about, you can explain more better way. Okay?
You got it.
This is just suggestion.
Okay.
So
Well-
from this information, I'm still a lot of questions, but
It's an interesting plot. Sounds like there's a lot going on.
yes, of
There's-
course, a lot of stuff going
There's a
on.
lot going on, yeah.
Yeah, and of course, I have no idea, something I don't have any knowledge, but roughly speaking, it's say a lot of stuff. So need to be.
So
think
do
about.
you want to include this slide for your presentation?
That would go great. I'd spend the entire seminar talking about this,
Yeah.
and I wouldn't even understand it. Okay.
Since you are wrapping
Yeah,
up.
but nice try to show the
Yeah.
equation. It's nice try.
Yeah, it's a.
Yeah, this one was a confusing one.
But nice
Anyway,
try.
just some quick last notes, some quick final comments from this paper was that although there are many unknowns remaining obviously regarding stratosphere-troposphere coupling mechanism, it is well understood that the tropospheric response is qualitatively similar across all timescales from weekly to centennial. What I mean by that is, for example, the tropospheric response from a sudden stratospheric warming event, which is on subseasonal timescales. The dynamical mechanism, supposedly, what this paper is suggesting, is similar to something on the seasonal scale, or on the yearly, or centennial, even. And apparently it comes back to that equation. And then, let's see, and I think that's it. Or, yeah, I think the point from that was that it might be suggesting that there's a single unifying mechanism across all timescales to describe this troposphere-stratosphere coupling. Nope.
Wait, so what's the paper called? I'm kind of curious.
Yeah.
This paper, it's a good paper. It's
So it's
just
a review
that
paper.
box was confusing. It doesn't even have that.
Is that the 2015?
Yeah, it's stratospheric influence on
Oh,
tropospheric
Kidston?
gestures. Kidston et al. 2015.
Interesting.
Which genre?
Nature.
Nature.
Kidston.
Kidston?
Kidston, yeah.
Kid, like K-I-D.
Kid, thank you.
Okay, good.
Good.
I met Charney's daughter at AMS. That was kind of cool.
Whose daughter?
Charney.
Charlie?
Yeah.
His daughter was at AMS. Yeah, I was like,
Did
You met
go
a
outside?
celebrity.
Is that the right one?
Okay, so like last week, I'm gonna continue talking about these mini lectures regarding INSO and equatorial waves. And so today I'm gonna talk about the vertical structure or modes in a continually stratified ocean. And so I might be even more confused than Henrik regarding this, so we'll see, hopefully not. Okay, so there's our topic. So today we're looking at the modes in the vertical structure. And then next week we'll look at the two-layer approximation. So this is getting closer to what we might think is more of a traditional INSO theory. Okay, so we're going to go back to our primitive equations in the ocean. And here we have our hydrostatic equation, our incompressibility, an equation of mass, and our momentum equations. And last week we looked at the momentum equations and looked at this term and made the beta approximation on this term. So today we're going to look at these variables like UV and pressure, or density and pressure here, and we're going to look at the vertical modes of these. So first we need to look at the boundary conditions of the ocean. So we have a free surface and a bottom boundary condition. The free surface means that there can be perturbations in eta, which is the height above sea level, above sea level, which is defined as z equals 0. And the bottom condition assumes constant height where there is no vertical velocity. So I made a little plot here showing kind of what we're looking at. The bottom boundary condition, W equals 0, Z is equal to negative H, constant height, and then the top condition is free, meaning that sea surface height can go up and down at Z equals 0. So in the continually stratified case, this means that density is a function of depth, meaning that there are many layers of constant density as we go deeper into the ocean, depending on height. So we're trying to describe vertical modes in the ocean where the Z solution is known. Therefore, our unknown variables are x, y, and t instead of x, y, z, and t. because we know z. And so if we were to look at our variables like u, v, and pressure, and showed it in this kind of vertical mode format, for example, we have our variable u on the top left of the equations, where n is the mode, and the fn is the eigenfunction. And I'm going to show on the next slide kind of visually what this looks like. So let's take, for example, our variable u. So I'm going to visually show this, so I do well with kind of at least visually seeing it. So here's our plane, our xy plane, and our time. We'll take t is equal to 0, for example, in this situation. And here's our negative u wind perturbation. So where it says u is equal to summation of un, which is a function of x, y, t, that's what we are seeing right now, our mode. And then the vertical structure is corresponding to the eigenfunction as a function of depth. And so here I just made up a kind of a function in the z. And so basically you could think of this as amplitude. So our mode never changes. The structure looks the same. It is one mode, but the amplitude, depending on depth, the amplitude of this mode will change. So for example, let's take this this xy plot of u wind perturbations, and let's assume that maybe it's closer to the top of the ocean. So maybe located right about here. Multiply it with the eigenfunction, you get kind of a certain amplitude of the u wind perturbation. As we get deeper into the ocean, this, for example, in the middle part of the ocean, the amplitude is at the highest, so this u wind perturbation will be amplified or enhanced. And we can see the pattern, the mode, maybe move in the xy, or move, what am I trying to say? It can move in a horizontal plane. Oops. Yeah, and here's another example showing maybe a dipole-like solution, dipole-like mode, and then the eigenfunction might have this wavy-like solution to it. So it just helps me kind of see it visually. And then all these equations, you can kind of do something similar to see it. But so we take all these variables, which we know the z, or the vertical structure, corresponding to a certain mode, and then we plug them back into our equations, and we end up with the following result. So now our momentum equations have a vertical structure corresponding to the subscript n, and we don't have to solve for z. So if we know, for example, let's take a look at our momentum equations. If you know the mode of the wind stress or the pressure fluctuation, you can infer the acceleration or horizontal velocity corresponding to that specific mode. So waves can travel vertically in a continually stratified ocean, which transports energy and nutrients. So we want to think about vertical modes in the ocean. And so next week we're going to look at the two-layer ocean instead of the continually stratified case, which is closer to ENSO wave theory next week. Does anyone have any questions? I'm still kind of learning this material, but.
We are also learning.
What's that?
We are also learning from you.
Okay, so.
Can you go back to the kind of theoretical model with the u perturbation? Okay.
This one?
Yeah.
Okay.
So this is a u prime perturbation. So this is a deviation from the time mean.
From the mean, yeah.
So okay, and
So
y, horizontal plane time.
Yeah, I just have time. I just have the u wind perturbation changing in the x and y depending on the time. But this
Depending on
pattern,
time, okay.
this pattern stays, or this mode stays the same. It doesn't. The structure of the mode doesn't change. It's only amplified, or enhanced or not enhanced depending on ocean depth, according to this eigenfunction right here that I plotted, and this. Yeah, so.
What causes the modes? Is it just like the same as atmospheric modes?
Yeah, kind of like if you did an EOF
Like a
analysis,
principal component, okay.
sort of something like that. But so here we have u is equal to the summation of all of the modes. So if you added up all of the modes, you would
Yeah.
get your kind of actual, or your U-wind perturbation. This is a perturbation still, right here.
Okay.
Does anyone?
Yeah, and why? So
No, you're good.
I'm confused about its
Mhm.
change in height. I don't know.
Okay, so
I don't
let's
see
just
that.
look at these two
Yeah.
plots, okay? So we know U,
Uh-huh.
we're looking at one mode of U.
Mhm.
So the mode meaning this kind of structure or this pattern in the XY, right?
Mhm.
So we have a U perturbation, just kind of a negative U perturbation, so kind of centered right here. And so this pattern, this mode does not change at all, like the actual, if you look at it. But the only way it changes is it's either enhanced or not enhanced depending on depth. So this is according to the eigenfunction, which is right here, f and z. So we multiply, depending on depth, this eigenfunction to this U-wind mode right here. So let's say we're 1,000 meters deep in the ocean right here, for example. That means that this value right here, we are multiplying to this mode, which corresponds to this kind of structure of the mode. So like for our example, 1,000 meters deep in the ocean, this U-wind perturbation will be enhanced compared to if we were closer to surface, like right here, because this eigenfunction, this number right here, is much, or it's not as amplified because it's a smaller. You can think of it as like a number. Does that make any more sense? So the U-wind, it's this mode is going to look the same throughout the.
It's like a barotropic.
Yeah, kind of like,
effectively.
well, no, not barotropic. So if it was barotropic, then this eigenfunction would be constant, it would be like 1.
Mm.
So you see right here on this plot,
Yeah.
if this wasn't curving like this and it was just one straight line, then that would be barotropic. But we're looking at a continually stratified ocean, so density changes with depth. So it's not necessarily barotropic. There is a case for a barotropic case, like I said. But in this example, we kind of have this curving like structure of the eigenfunction that when you look at it through depth, and so that this pattern, as we look at it through depth, this mode will either be enhanced depending on where you are or how deep you are in the ocean. Does that kind of make sense? So like in meteorology, we might think of like a stacked weather system, like low pressure at the surface, low pressure aloft. It's kind of vertically stacked, and then you apply an eigenfunction to it, and that structure is the same throughout the entire atmosphere, but it might be enhanced at a certain level in the atmosphere, and that's what this bottom plot shows. So that's just an example, maybe.
So I'm wondering,
Mhm.
how do you calculate the eigenvalue? Did you
Um,
have all the data sets for all?
I'm taking these variables and equations from a book, so I'm not calculating. I'm not actually
Okay,
calculating
you just
any
got it from
eigenfunctions.
the book.
Yeah.
Okay, so I just wondering,
No,
did
no,
you
no.
get all those data sets?
Yeah, no, I'm not working with any data
Oh, okay,
sets.
okay,
I'm just
okay.
for me. Oh, so you weren't here last week. I'm kind of I'm kind of trying to enhance my knowledge on
Okay, okay, I got you.
on oceanography.
Oh.
Per my committee, they wanted me to kind of learn a little bit more, and so I'm trying to.
Okay.
I'm kind of practicing what I'm trying to learn, just in kind of more of a lecture-ish type of setting.
So you need to teach it, or what?
So the committee wants me to. My committee wants me to give a 30-minute lecture regarding these
knowledge.
several topics
Okay. Oh, okay.
with wave theory and ENSO. So, yeah, I'm trying to learn it. It's.
Oh, great. Great.
I had never taken a class on
Yeah,
oceanography
because
before, so
I
it's,
know those data sets is difficult to get.
yeah,
Yeah, so-
especially for me.
Yeah. Okay. Go ahead.
Okay, so yeah,
So just quick one. So everybody knows the EOF, right? In the EOF analysis for this class.
Empirical orthogonal
Yeah,
function.
people do it. So based on that knowledge, can you explain your result? Okay, your example, Jacob asking.
Yeah. Well, I tried to explain it. Let's see here. What do we got here? Okay. So our n refers to a specific mode. And so, for example, if you were to take the EOF analysis, I might be explaining this wrong, so correct me if I'm wrong. But
Just try it.
okay, so if we take an EOF analysis, we have kind of the leading mode of variability, the second mode of variability, a third mode, and so on and so forth, you know, all the way to however you define it. Could be, 100 different modes, you know? So the leading mode of variability might look like this sort of pattern and this sort of structure in the Z. So at least for me, when I do an EOF of sea surface temperature, we're looking at one plane at the sea surface, and this is what it might look like, this monopole-like structure. If I take the next EOF mode, maybe it looks like this dipole structure. And so the next EOF mode might look something very different. And I think N is corresponding to those modes. Yeah.
So I just educational, okay, just
No, yeah.
educational support. Okay, so in the EOF, people use, for example, you have SSD and they usually X, Y, T, right? TXY is better. So
Yeah, it doesn't matter.
you have a time, lat, long, right? And people try EOF for this one. And what you get is first mode, you get SSD pattern. That means only lat and long. And you have a time series, PC time series, that one the PC T. So EOF just decompose spatial pattern and time, right? So you combine, just decompose two components and see how it looks like. So pattern is fixed and based on the time, which year is positive, which year is negative, right? So EOF just decompose two components.
So we have 4 components, and we decompose to 3, and then our Z
Exactly.
is, okay.
So in Zach's case, they need to think about propagation of the pattern. So his case, this is his F and Z. And this is his U, X, Y, T.
Right.
Okay? So in the vertical amplitude is just only coming, it's like a PC. Same thing, just only decompose. So maybe for you,
Yeah, no.
for this kind of stuff, maybe understandable probably. But for the Zach's case, it's more general. So probably you cannot use this explanation.
Me?
You cannot use
Oh
it.
no, it's good for me
You
just
cannot
to.
use it. But this is for people already know what is the EOF
Right.
analysis for the climate science. So this sounds good?
Yep.
Okay. Okay, good. Just educational help.
All right, well, we need to talk about weed now.
Where's Larry? We need Larry.
No,
I could get him for you. Want me to?
he's not here actually.
Oh.
I'm going to give just a quick update on our CAST project because I have a couple questions about analysis that I think y'all could help me out with. So just as a quick background for folks who don't know, I'm working in a group to quantify or determine the effects of climate change on water availability for cannabis cultivation in Northern California. Cannabis cultivation in that region accounts for about 60% of the national product, so it's a huge region in the area, and it's growing rapidly with more legalization, medical marijuana becoming more legal as well. So there's a lot of interest in understanding how much water this practice is going to take and whether it's kind of sustainable, that's the buzzword, in a future climate. So the way that we're doing that, sorry, now I'm just getting to the slide. The way that we're doing that is by looking at stream flow, because all growers have to divert water, and they mostly divert surface water. So they take water from a nearby stream, but they can only do that when they're legally permitted to do so. So in order for them to divert water throughout a year, the stream flow has to be adequate for local ecosystems, fish, and upstream users, primarily agriculture. So there's a lot of things in the equation of whether or not they can actually take surface water. So our goal is to compare and try and see how the surface water flows have been changing and how climate relates to that. So there's 19 USGS gauges that cover the Emerald Triangle, and from them we can get flow metrics like total amount of runoff, total amount of water coming through the system. I'm not a hydrologist, but they seem to know what they're doing. So this data was given to me by somebody who looked at all of these USGS gauges. And what we're looking at is actually a product of a functional flows calculator. So they use an algorithm to determine how many days per year cannabis growers can actually divert water. So it's based off of the monthly flow compared to the annual flow. So they're constantly checking monthly flow data and comparing that with annual flow data, and from a historical standpoint as well, and saying yes you can divert or no you can't. Does that make sense?
So please educate me. Okay, I don't know. Okay.
Yeah, I was.
What diversion days? So what water diversion?
Diversion is like taking water from the stream. So they'll just put in a pump.
Activity or
Human activity for cannabis
Okay.
cultivation.
Okay, human activity. So it's a
For
120 days is
irrigation
human just
purpose.
Irrigation, but they're not. So they pump the water and they store it.
Okay.
There's a lot in between.
So if it's 0 day, that means nobody used the water.
Nobody that was growing cannabis was legally allowed to divert water.
Nobody at all.
So
Okay.
but then 140 would say that you would imagine, oh, there was good snow, there was a good, we had a good water year, so there was enough water, and they could divert for about a third of the year.
Okay, so
Do they have how much water they divert? Do they have their data? Like
We're working on that, but the problem is that it's only been legal for a certain amount of time, and they're not keeping track of that.
I see. Okay.
So our this is kind of a zoomed out perspective of how are just water availability changing. But diversion days is useful because this shows just effectively how long they're legally allowed to take water.
Is this for all agriculture or just?
No, only cannabis.
Oh,
yeah.
so who's on the top? Like who gets first dibs?
I'm
Just
sorry. These are great
Oh,
questions.
I'm just curious.
But I don't know. Actually,
I mean,
fish.
generally traditional agriculturalists.
that's what I would.
But I think
You
in
think
this
so?
sense,
Yeah.
Okay.
Yeah.
in this sense, in this region. There's a lot of endangered salmonids. So their biggest concern. It's not a very big agricultural region.
Right.
Obviously, the Central Valley is, but this region is west of the Sierras. So
I'm just okay. So is it one river? Sorry, I don't know anything about
19 USGS. Sorry, I should have had a plot.
This. No. I'm just curious.
But
Like,
yeah, it's not one river. There is one main river and then a lot of tributaries.
Okay.
And then, sorry, so this is cannabis draw specific?
I believe so. I'll
Back
check
in
that.
The 1980s?
Well, no. So this is we have streamflow gauges from the 1980s. What they currently use to determine the legal diversion days can then be
It's an algorithm.
it's an algorithm.
Gotcha.
So yeah, just
Okay.
depending on the stream
Gotcha,
flow.
gotcha.
Yeah.
and
This
is
is an
that
algorithm that was created more recently that has been applied. Like this is what the data would look like if it had been drawn back
Yeah.
20,
well,
30 years
so
ago.
exactly.
Okay.
So what is different color?
Yeah, I was just getting to talk about this plot. So the different color is all the 19 gauges, and then the dark line is the average. So you can see there's generally good agreeance. And this is a correlation matrix of all the different gauges, because we were originally thinking we would have to analyze each individual gauge. But when you think about doing that on a climate perspective with a 2.5 degree grid box, that doesn't make much sense. So this is my argument of saying we don't need to analyze each gauge, because we're seeing that they're very well correlated, right? So we can just look at the average.
Mhm.
So I've now taken that big solid black line. We're thinking about removing this gauge. You can see that there's there was probably a major upstream change where we're seeing really big differences in the diversion day mean before 2005. So we're thinking about removing this, but I haven't done that for the following analysis.
So just quick one. So
Mhm.
in the low number, just kind of indicate a drought year.
Exactly.
Okay.
You can think of it that way. Low
Yeah, just
number,
think about it.
low stream flow,
Okay.
drought year.
And the high number, the more water available.
hmm So I quickly compared them with just canonical teleconnections. So we're looking, the top plot is the blue is diversion days, so the bar in the back is diversion days. And then we have the 4 different ENSO indices. And you can see the 1+2 region actually correlates significantly. And then on the bottom in panel B, we're looking at diversion days compared with more northern hemisphere variability. I have the PDO on here, which maybe doesn't exist. How's that? But then PNA, AO, I did the NPO and the NAO, but those are just manifestations of Arctic oscillation anyways, so their change in time is the same. So mostly just look at the PNA and NAO. And we can see that really these northern modes aren't explaining much variance or not correlating well with the amount of diversion days, but there is a relationship with 1+2 ENSO. But when you take, again, that diversion days time series and correlate that with the geopotential height field, what we see is a lot of the dipole pattern. So the negative relationship in the west indicates that pronounced ridging creates lower diversion days, so less amount of water in the system, and coupled with the opposite pattern in the east. So the dipole is correlating quite well. And again, from the SST field correlation, you could see the ENSO 1+2 region is highlighting pretty well. We also have this region in the Gulf of Alaska, but that could be a product of the atmospheric circulation, so probably we'll only focus on the 1+2 region.
Okay.
So the original purpose of this project is to compare how much atmospheric rivers are actually
This one.
creating these differences in diversion days interannually. So I developed my own tracking mechanism, but then realized that the ARTMIP, are you familiar with this?
Tracking missile?
The ARTMIP, the Model and Comparison Project? Okay, so these guys, it's a review paper. They compared about 25 different tracking algorithms. They consolidated all of them and did them in NASA's MERA. So they used all the different algorithms in one data set. And they have a published,
All right, I'll see you later.
Yeah, see you then.
published gridded output.
I need to go,
Yeah.
Jacob. It's
Great.
good work, so.
Yeah. See you soon.
Yeah, see you soon then.
So they have published gridded
Okay.
output. It's all NC files. You could compare effectively 25 different algorithms in a snap. So it's all binaries, 1 if there's an AR, 0 if there's not. It's pretty brilliant. And so I downloaded this data and checked it out. I haven't compared it with my tracking yet, but the inter-algorithm variability is quite high, as you can see. So these are number of ARs, landfalling ARs in the Emerald Triangle per year. And so I've detrended them just so we could get a better idea of what's actually going on. But you can see still, I mean, huge numbers. It was capturing, some of these methods were capturing upwards of 300 events in a cold season, which is quite unrealistic. So what I don't know is, how do I use this? You know, because
Wait, Jacob, I have a question.
yeah.
So has anyone looked at? So you're looking at river. You're looking at? Okay, remind me again. You're looking at like discharge in a river or
Diversion days. So it's more of it's more of a social metric too. It's
Okay,
not
so-
simply
Okay,
Bio.
I see. So have you? I'm just thinking. Are there I can't remember from the previous plot. Like, what's the power? Like, how are the oscillations of this river flow?
So it's not. This is not river flow.
Okay, so this is just this algorithm.
Diversion days.
Diversion
So
days,
It's
I see.
Yeah, I mean it's based
Based off of this algorithm.
off of flow in each individual gauge. So they
And does this time series correlate with how much water there is in the river?
Absolutely. So it's a function of the monthly annual. I should have the total flow as well, but it's a function of the monthly flow.
I'm curious. So does this correlate with? Has anyone looked at like soil moisture maybe?
Yeah. So that's why. Yeah, but then so when you start to think about soil moisture, topography, land use changes, you're starting to get into a lot of things that we don't have the time, energy, computational skills, or data to fully understand for this region. You know. Yeah, soil moisture is definitely a part of this, but that's not accounted for in the functional flows calculator.
Okay.
That's a good question, and we've thought about that, but we've deliberately chosen to not, because it's kind of a deep dive. If you start going into soil moisture, then you need to know topography, then you need to know, land use changes, and I don't know.
Huh.
So, and that's probably why, if you look at this, why you see that the dipole pattern actually has a pretty strong correlation is because this is influencing the temperature of the region. This is influencing, it probably has an effect on soil moisture, precipitation in general. If you have a big ridge in the west, you're blocking the incoming atmospheric rivers or the incoming extratropical cyclones. So that's probably why the dipole pattern shows the relationship, and some of the others don't, because this has would have more of a holistic effect on the region.
So for me, at least since it's in Northern California, I would expect the region directly above it and nearby it to be very highly correlated.
Yeah, I think that's a good point too, but if just the general circulation feature associated with this, you can imagine that, pronounced ridging here is still going to park or block a lot of systems coming in, and it's still going to give you a ridge of high pressure that's in that same area. Well, yeah, it is kind of cut off, and the northern, the Emerald Triangle is right here, so it's not at the epicenter.
It's at the 300 millibar level, so I think that's why that explains that.
So Jacob, in your result you show that the diversion days is highly correlated just with the North American dipole.
Yeah, well, so far, and the Nino 1+2.
Oh, 0.3.
So,
also Nino 1+2. Okay, so
Which
can we
is
say that those drought year also have the high correlation with the North American dipole?
yeah, and I think that's a good question. I think Simon's done his drought to deluge paper, talked about the effect of the dipole on California precip.
Okay.
And his argument too was that, ENSO isn't the only thing explaining precipitation regimes in this region, so we need to look at other things. And now the motivation for this is everybody's looking at atmospheric rivers. They're like, okay, these things are what's causing all of the changes in California precipitation and California water trends. But that might not be the whole picture either, or the best way to think about it. So what I was trying to do is show.
So did you consider the whole picture? So consider all of the factors, and then you got the result that this is only highly correlated with this dipole.
Kind of, yeah. I think there's more I could look into, but the goal is to show contribution from general circulation features, modes of variability, field variables, geopotential height and sea surface temperature, and then also show contribution of individual weather events like atmospheric rivers. Because we can track those, I've developed a tracking algorithm that works quite well.
So
but
you developed this algorithm to track atmospheric rivers?
I didn't develop this one. This is from a review paper, but I showed it probably a few months ago. I've got results for my own algorithm as well that's derived from one of these methods, so I'm going to compare them. The problem with
did you already generate your figure to compare with this one?
No, I haven't yet, because I still don't know how to even analyze this, because I don't know, do I compare my figure with the mean? Do I compare my figure with a subset of the different algorithms that are performing similarly? That's what I wanted to ask y'all. I don't really know how to section, sorry for the long drawn out thing, but I don't know how to section this off into anything meaningful, because you could, from your eye, you could quickly pick away a couple different methodologies that don't correlate with the other ones, but does that mean that this is kind of the model problem, right? The ensemble problem. Does that mean they don't have useful information? I don't really know how to threshold them, or just can I take the mean? Is that fine? I don't. I just don't understand.
Yeah, good question.
Can you go back to the tiles? So if you eliminated some of those other tracking methods, what you're saying is that you could demonstrate greater correlation to yours,
Not to
right?
mine. So
or
these are
to the one you're looking at.
These are the inner So this is a
Right.
correlation matrix showing how each one relates to all the others. So you can imagine here, Will, whatever, I'm not going to say that, is the correlation with the AR Connect method. I know all the names are terrible, but that's just what they are. You can see that correlation is low. It's,
Right.
And so this color denotes that none of them are statistically significant, whereas anything that's has a darker color means that it's at least statistically significant. So the idea I was thinking is, okay, well, I could take out Will, I could take out LBNL, Shields, AR Connect, so I could remove 5, and then I would have only these methods that related to each other well. But am I missing out on important features by doing
Right.
that?
Right.
Is the question. And I don't know.
How do people? How is that usually handled?
So that's
So usually tracking is pretty tricky, and it's also depend on which location you are using and which kind of phenomena you are focusing on. And then it's really depend on what criteria you use and what variables you use. So that reason why it's pretty diverse. And then there's no single perfect method. So people need to adjust based on their purpose, and then validate it, and then believe, oh, my method is applicable for this case, but no guarantee to other cases. So I don't know low correlation, how do they develop it? Everything focus on the atmospheric river, or
So they're all methods that use integrated water vapor and integrated vapor transport.
yeah, but the question is just focus on the atmospheric river
And the purpose is solely for atmospheric rivers.
for only the western U.S. coast.
I've removed the ones that don't have that region covered. So there's a couple that are for like South America or Europe.
Yeah, so some
and
people
those
just
aren't-
try different location, right?
Yep.
And then in that case need to change the different criteria. So yeah, it's really hard to check all of them, of course. But
Yeah.
but maybe some good one, maybe only focus on the California region, maybe, and then skill maybe high.
So you think I should see which ones? So this was published in 2018. I actually haven't seen a paper that's used it.
Oh, this isn't your figure.
This is my
Oh,
figure.
Oh, this is your figure.
So
this is
they
your figure.
provide the data, but they
Oh.
don't. I still had to process it so that it's only looking at landfalling ARs in the Emerald Triangle. So they give you gridded NC output, which is useful, but in order to get a frequency for a specific region, you still have to loop through all the data and program that. And so that's what I've done here. Each one is how many ARs hit the Emerald Triangle in a year for each algorithm. And then I'm showing the relationship between them because I was trying to figure out which ones I can use.
And then which one do you want to use?
I don't know. So I really don't know. The mean seems like the most attractive option to me, and maybe that's wrong, but like it'd be hard. Some of these I feel like I would just want to pull right out, like this green method that that many atmospheric rivers in a year is just not reasonable, So
Oh, this for the landfalling ARs strictly in the Emerald Triangle?
yeah,
Can you go back to that plot again?
this one.
Yeah.
So
A lot of them seem really high. I think on average there's like 6 or 8.
Well, yeah, and then I wish I could zoom in, but some of these, probably more reasonable. When you think about how many atmospheric rivers they're getting in a year, it's anywhere from like 5 to 15. 15 in a cold season's a good amount. So,
15's pretty rare.
but still, the lines that are right next to the 0 mark in the detrended space are probably the most reasonable.
Probably.
So can you just go with those then? Can you just go with the ones that are between like here and here?
I don't know. That's what I mean. I feel like
I mean,
No,
under the
'cause-
assumption that the other ones are a little unreasonable based on what we know about the number of atmospheric rivers, right?
true. So the one thing I do need to check is that they're all standardized from a time perspective. It shouldn't be a problem with the way that I process the data, but if they don't have a time criteria for their atmospheric river metrics,
Mhm.
then I would have to add that in myself, which I haven't done yet, which could explain these super high values, but
What about like extreme precipitation days in that region? See how well it correlates with some of these lines, maybe.
with the atmosphere,
Well,
yeah.
Yeah,
And
just
that-
to see like which ones are crap, you know.
Yes.
Like,
Well, which one is most correlated to your diversion?
Diversion days, I haven't done it yet because
Okay.
I don't know what to take from it. Do I
So-
just use the mean? Do I use them all?
We have this
I could do a
functions, right?
correlation matrix.
Yeah.
I should have done that.
And you just pick up most equal one.
I should have done that. Yeah.
Is there somebody with a strong opinion on which ones of these are crap?
Well, this is why. So what was kind of curious, and maybe just because I've worked with it, but the metric I've looked at, because I've been able to visualize each atmospheric river that it tracks, and they look very reasonable. You know, it looks like you could see the system moving in. The numbers we're getting per year make sense. So I don't know. I just don't. I would almost rather use mine because I've just visualized it all and I've seen through the whole process.
but these atmospheric rivers don't necessarily mean like any rain in the region, right?
Exactly.
It
So-
just is high moisture transport, right?
Yep, and that's what I think it's going to end up showing is that everybody's talking about how atmospheric rivers drive precipitation regimes, which they do, but at the same time, in the context of general circulation, right? They're influenced by the presiding conditions over the wet season. When what you're looking at in the geopotential height field for DJF is going to have a huge influence on
So
how
if
your
you,
atmospheric
if you
rivers are.
mapped out all of the atmospheric rivers that didn't produce precipitation and took those two data sets and looked at those more carefully, maybe you come up with a result.
Yeah, that's just
I
that's
don't
a lot.
know.
You know?
Yeah.
Do I mask out in all 25 algorithms and then
Yeah.
So, Jack, I have a question
Yeah.
for you. How do you exactly define the atmospheric river
So,
landfall?
I'm a little jaded about the definition, honestly, because it's just the it's the warm level jet in an extratropical cyclone, and so that's the problem is that they all have different definitions for what an atmospheric river
Yeah,
is.
which region the moisture come from? Did you define is the atmospheric river?
So it's a tropical moisture source, but
Yeah.
any extratropical cyclone in the mid latitudes mostly is getting its moisture
Yeah,
from the
right.
tropics.
How do
So they define it
need
by
to-
the length and the width sometimes. Sometimes they only consider length. And then they need moisture transport values. So really the only new thing about atmospheric rivers is the way of looking at them. It's not that they're new phenomena, it's that we now track them using integrated water vapor and integrated vapor transport, which
So,
previously wasn't as
So
new.
did you
How do you mean new?
choose is that season? Do you separate it from maybe tropical cyclone or something?
Yeah, there's no tropical cyclones in this.
Oh, you already separated.
Yeah, there's no way they're in this tracking mechanism.
Mhm.
Yeah, the tropical cyclones aren't in it.
Okay,
And
wait, I have a question. So,
yeah.
so these ones that are 150, like, is it just 150 3-hour? Like, is it?
That's important to realize. These are 3 hour. No, but the way I wrote my code is that it's filtering through, and if it is only retaining one binary 1 for an atmospheric river event.
So it could have just been one 3-hour atmospheric river potentially.
That's
or
what I
at
was-
one point during the 3 hours.
That's what I said. Yeah. So when I was talking about if they don't have a time definition already, that's where
Did you
that
drop
could come from.
You dropped the ones that didn't have a time definition.
I haven't dropped because I need to comb through 25, read the paper, and see how they did the tracking.
Yeah.
So
That sounds like a lot of work.
Yeah, I just haven't. Yeah,
But
but
yeah,
from
there's
the-
some things that you could probably drop out just based off, and then you could in the paper you could explain why, and I think that would be okay, maybe.
And I think what I'm going to end up doing is just using this as a way. I'll compare both methods, so we can say we compared. I mean, it might just be useful to say that we compared this tracking algorithm with the ensemble or the mean from ArcMIP, and it was reasonable. And that's, I mean, we did our due diligence then, right? What else do you do?
Yeah. Another concern is this algorithm maybe for NASA. Usually only use the NASA metadata, right?
No, so they all develop them in different data sets.
Yeah, it is different,
Oh.
but this algorithm based on the NASA Mera data.
So it's all in NASA's data.
So put the same data and then use a different algorithm and get this value, right?
Same data, different algorithms.
Yes. So this is probably just only the mental problem. So if you're a developer of the algorithm, and if your correlation looks, your method shows a pretty poor correlation with others, and then probably you will claim, hey, I don't believe NASA meta data.
So they were
if
all
you use different data, my
yeah.
stuff is more better.
Yeah.
Right. So maybe you just use what? So you probably you have a data, right? What you want to use, observation data or reanalysis data, and then using the same data set, and then some paper totally have the same method based on develop a method based on such kind of
Based
data.
on NCEP,
NSEP, well,
which is
yes,
what I
right.
produced.
And based on the NSEP, so you just use their method, it would be more make sense for me.
Yeah.
So this is also fine, and if correlation is high,
We can say at
it's,
least
yeah, so
the
it's in the
responses.
algorithm. So it's still pretty diverse in the algorithm, but this method is kind of reasonable compared to
Okay.
others. So maybe fine or something. So
Yeah, I think that's what I'm going to end up doing because that sounds
Yeah.
better than combing through and filtering out each algorithm's output.
yeah. So my concern is if you pick up, oh, I think this is better, best one, but it's not necessarily it's applicable to your case,
Mhm.
right? So
Yeah.
So
And I say new, sorry to answer, but it's only new
That was, wow.
because atmospheric rivers are not new, but with modern data, satellite era data, the way that we can look at moisture transport is
Right.
different. And so it's a very
I was
trendy
just like,
research
when
topic.
was that change?
It's still happening. I mean, the
Okay.
whole people are just. It's a very trendy research topic.
Gotcha.
Atmospheric rivers in the east, in the west, in Europe, in everywhere. You know.
I'm shocked that you held that question in your head for 4 minutes, and that was impressive.
Okay, I can stop talking now. But
so, did they provide the tracking algorithm in their paper?
yeah, so they have
How many algorithms? they
there's
provide?
about 25.
25. Oh, well.
Yeah.
Yeah. So, Jack, you said you already finished the developing the tracking algorithm for the atmospheric river.
Yeah, I
right?
did my own.
So you do it for the atmospheric river. Landfall. On which place did you do it for the Utah?
No, for the Northern California.
Oh, Northern California.
So the Emerald. It's
So-
called the Emerald Triangle. It's where all the
Oh, Emerald Triangle.
Yeah.
That's Northern California.
Mhm.
Okay. So I would like to do the atmospheric river, how they relate to our precipitation extreme in Utah. So
you can use. I would try using this
using this
first.
first.
I can also share with you my grad's
Okay.
code that's
Yeah,
doing
yeah.
the same thing.
Yeah, great. Please.
But what's nice is that you pick a spot and you say, and then from there it tracks only the atmospheric rivers that hit that location.
Oh, can I do that for the whole Utah?
You could draw. I mean, you can define your grid box for however big you want. And I've got everything in Zion already. So all the data from this catalog is on Zion. So
Okay.
if you want to use
Yeah,
that,
yeah.
it's
I
really
want to
easy.
use it.
Yeah.
Yeah, great.
Mhm.
Thank you.
Oh man, I gotta move my computer. Oh, I need the one that. Oh, that's right. That's the short one, right?
Which one do you need?
I need the one that goes into the USB.
It's
I
a
think
real
it's
thin,
universal. Yeah.
like kind of a. I don't even know.
But I think it's a short one to have to.
yeah.
plug
Is it this?
in.
Yep.
Yeah.
Is it HDMI? Yeah. Okay. I can also move if you want.
Nope, we're good. Nope.
I know.
No.
Yeah.
Sorry.
Oh,
Last
is that
week
a
I had to go
different-
over there because it was.
Okay.
super fast today, hopefully. Hey, there we are.
That's what I thought too.
Ta-da!
So I put together, I don't know why this looks like this. You don't need to look at my face. So I I signed us up for this workplace thing by Facebook. It's not Facebook. You don't need your Facebook credentials to log in. You only need to accept the invitation that I sent out today. But the functionality of it works a lot like Facebook. So for those of us who are used to using it, it'll be really easy to inherit, I think. The key with any of these things is just going to be users. If we don't look at it, it doesn't do us any good. If we don't communicate through it, it doesn't do us any good. So it's all going to be about whether or not we use it. I just downloaded the app. I haven't gotten a chance to play with it yet, but the app gets really good reviews as well in terms of functionality. And then if you have the app, you can also set yourself to alerts, and that way, you can even turn off alerts. So if you're like, I don't want to hear from Yoshi anymore, you can shut him down, which is great. Okay. So I wanted to chat today about a few stories in the news. I don't know why this is all small. Okay, so continuing what I started last week, and I'm going to try to do this every week, is just bring a couple of stories to you that have been in the news where climate science is either being referred to very specifically or tangentially. Often, as I'm sure you guys all know, when climate science, when pure climate science gets a nod at all in the media, it's usually because it's been incorporated with some other science. Some other scientists are doing something. They're like, oh, climate has something to do with this, because these days all science is climate change science. So the first story I want to bring to your attention is this piece from Scientific American about a recent study that shows correlation between warming waters near the shores of California and whale entanglements, which is when whales get caught in fishing nets. And what happened is that during these heat waves that were recorded from 2014 to 2016, krill populations fell. That's humpback whales' favorite food, and so they went searching for other food. The other food they went searching for were anchovies. Anchovies are closer to the coast, and also anchovies are one of the active fisheries off the coast of California. So all of a sudden they were running into fishermen nets, and this is because of something called habitat compression, which has been really well studied in terrestrial ecosystems, but is increasingly being studied in marine ecosystems. And this is basically just like it sounds, habitat for different organisms starts to compress. We put all those organisms into a smaller area, and because of that, their interactions with each other are aggravated. In this case, the organisms are us and whales. Here's from the study, you can just look at the warmings that they were looking at. This is the top four are March and the bottom four are May across a number of years. And so the thought is, okay, well, if this happened during these unique warming events as we warm more consistently over time, and this is not just normal variability as it is aggravated by climate change, whales are going to start running into fishing nets even more. And you're going to end up with things like this. This is a fisher or a rescuer trying to disentangle a humpback whale from a fisherman's net. Okay, so why do I think that we should care about this? I think we should care about this because megafauna, really large animals and organisms, or charismatic fauna, those sorts of animals that we've attributed human emotions and personalities to, are really, really good ambassadors for every other form of science out there. I can't get people to care about aerospace engineering unless I start talking to them about peregrine falcons, in which case I can capture their attention immediately. It's pretty amazing. And it is absolutely incredible what charismatic fauna can do as ambassadors for every other science, including our sciences as well. And in fact, I even wrote a book about that. So, plug for that. Everybody's looking.
Amazon, $29.99.
And you can order. I will bring you a free copy if you want. It's not like it's gonna hurt sales or help sales.
You get all 1%.
Yeah. It's like, oh, I'll buy the book and support you. It's like, no, really, buy me a cup of coffee. That's like more money than I will make from selling the book. But thank you. But look, so I wanted to bring this up as a way to help us think about ways to communicate the importance of our research, or to just not even communicate what our research says, but just to start thinking about what are the entry points that I can have with average ordinary human beings when I'm talking about my research. So why should I care about a drift-free decadal climate prediction system for the community Earth system model? Well, because we're talking about warming of oceans here. And let me tell you what happens when our oceans warm. Well, here, this is what happens when our oceans warm. And it's an instant connection point that people make to something that they actually care about that. You don't have to look any farther than the wildfires in Australia to see this, right? You guys have all seen the billboards now where people are collecting money, right? Wildfires are nothing new in the American West, and we can't collect a goddamn cent to help human beings. But they happened in Australia, and koalas started getting burned, and all of a sudden people cared. It's tremendous what these animal ambassadors can do for us, or at least as an entry point to start having communication about this. All right, so the other story I want to talk about comes out of Utah State University. This is Tammy Rittenauer. She's a paleoclimatologist and geologist. She's kind of awesome. And she was part of a team that got to get a look at these sediment core samples that came from a almost mile-long core that was extracted from an old Cold War base in Greenland back in the 1960s. This thing got stored away for many years. People forgot about it, and then all of a sudden it kind of like got unearthed again, and people said, oh, what can we learn from this? And of course, it's not very common to get a core sample from under the ice sheet in northern Greenland. There's not very many of these, let alone from that long ago. And so Professor Rittenauer applied her method of evaluating the ages of soils, which is called optically stimulated luminescence, in which you take basically it's a way to gauge when the last time certain minerals were exposed to light. And this is the really fascinating thing. What she found was, at least preliminarily, that the samples had been exposed to light 400,000 years ago. Now, I talked to her yesterday, and she said actually it's probably 600,000 years ago. Either way, that sounds like a really long time until you realize the fact that the conventional estimate was that the ice sheet had remained intact for more than 2.5, or for more than 2 million years, probably close to 2.5 million years. And what this means is that the Greenland ice sheet might be more vulnerable than we even recognize. And if so, it means it could melt faster. If it melts faster, of course, our seas rise and we all die, at least those of us in Miami, which you may or may not care about, except for, isn't that where the Super Bowl's being played this week?
I don't know.
Okay. Anyway, those are the two stories I wanted to draw people's attentions to. I'll bring one or two every week and just talk about like how climate science is being framed in the mass media. And then increasingly, as I come to understand all the research that y'all are doing, I'll be able to help maybe position some of us to figure out what the best placements for our findings are and the best stories to tell. Is that helpful? Actually, by the way, I should ask that before I just assume that you guys like give a shit.
Yeah, oh yeah. think
I
we
just
get it.
learning, so really helpful. Yeah.
It does sometimes feel like it's hard to, a lot of study efforts nowadays are very niche. So
Yeah.
what the media cares about isn't always the fine details of our model biases that are really, really important for the community.
Right.
You know, incredibly important, but maybe not important to the average.
Yeah. So what I want to, what I, you know, I was at the AAAS conference last year, and I talked to a bunch of scientists about that very thing, right? Like they're getting pushed to do more science communication, but they're like, I can't communicate this very, very simple, like not even simple, this very, very complex thing. And it's not about the complexity, it's about the specificity that makes it hard to communicate. And so what I'm trying to help people do, what I'd love to be able to help this group do, is identify those opportunities and say, okay, you're right. This thing, nobody from the New York Times is going to come talking to you about this thing, right? But if we can develop a conversation about this thing and then tie it back to the research that you're doing, it becomes an entryway for that conversation. And expose, and little by little, we expose people to the specificities of what we're doing.
Okay, still generating the PMP, the figure for PMP paper. So right now I've already generated 24-hour 100 square mile PMP in Utah based on these 3 data sets: NARR, Precision Stage 4, and the station data set, because our station data set that we downloaded before had some problems. So as we re-downloading the station data set, and right now it's still in the data manipulating stage. So this is the these 3 data sets show the PMP from 1981 to 2018 for this 24-hour duration and 100 square mile. So from the NARR, it shows from 2001 to current, it shows gradually increased PMP value, but from Precision and Stage 4, it shows the contrary result. So this is for the whole season. Then next step, we separate this to the different season from spring to winter. So this is for spring. We see from spring, these 2 data sets is show increase in PMP from 2001 to current. Also the stage 4 also saw increase from 2001 to 2015, but because we only for this period we only have 2 years data set right now, so we can see that this maybe not correct, maybe cannot reflect the whole 5 years. So
Can you make it every year, or is it better way to every 5 years? Just wonder.
yeah, this is every 5 years.
Can you make it every year?
Yeah,
Oh.
can every year, every year, right. Yeah, maybe I can add every year value on this clock also.
Yeah, we also probably interesting.
Yeah, maybe. So, but generally from these 3 data sets, we've seen an increase in PMP during spring season. And let's see the summer. From this 2001 onward is in decrease, and present also decrease, but for the stage 4 it shows different, it shows increase. So So, so let's just see the autumn. Yeah, autumn. NARR shows increase, prison shows decrease, also stage 4 shows decrease. And the winter it shows also increase from NARR and increase for the prison, but decrease for stage 4. So, so we show this from all these data sets for this different season and for all season in this table, and then we can get some conclusion. So for spring, all these three data sets shows increased PMP during from 2001 to 2018. For summer, these two data sets shows decrease, but stage 4 show contrary result. For autumn, prison and stage 4 showed decrease. For winter, these two showed increase, but stage 4 showed decrease. So, in general, for all season, only NAR show increase, but prison and stage 4 show increase during from 2001 to 2018. So, from this table, we can find that if we use different data set, we will generally get different results for our PMP trend. So right now I'm still dealing with the data quality issue with the station data set, and we will see what the station data set show. So basically, we will believe in station data set. So this is it, and our next step we will generate for the different duration and different area, and also right now I am dealing with the data set that we just downloaded. Also, I got another data set, GSOD. I want to add extra information to our station data set to see what the result will be from this station data set. Okay, that's it.
Do you think that's a product of, that's totally a data artifact, the differences in trends, right?
Yes.
Yeah.
Yes.
Is there a deficiency? No, I'm not saying the PMP calculation is wrong, but would there be a better way to get the same information that would show more agreeable results?
Oh, you mean that do we have better way to show more consistent result?
Yeah, I'm just curious. It almost seems like maybe this PMP in itself isn't the best way, because this is what they use to make a lot of engineering decisions too, right?
Oh, you mean the PMP isn't the best way, but what we need is we need PMP.
We need it. Okay.
Yeah, we need PMP. This is the project that we need to recalculate the PMP in Utah. So PMP is the result what we need.
Okay. Yeah, and I don't know if it's good or bad. I'm just curious.
Yeah, I know. Yeah, I know. So we just waiting for the station data, for the result of station data. That will be, because mostly we believe in station data set. Yeah, but yeah. So different data set, they have their problem also.
Yeah.
So stage 4 includes most of the data set, the data source, but at the same time it will cause some problem. Yeah. Also, so yeah. That's it.
Do you have something for this? Yeah.
Okay, so I'm writing, I'm not writing anymore, I'm revising a paper, and so I don't really have that much to show right now because I'm working on the writing part of it. But I'll just show some supplementary figures that will go in it. So one of the comments from the reviewers was that, you know, maybe GPCC data is not reliable enough because of the sparse stations in Tanzania, which is true because there are really only 7 stations, and they're mostly concentrated in the east and mostly northeast, but there are some areas that are pretty bare, you know, in terms of observations. So the plot is just to show where the stations are and how many observations there are in the country for the study period. So that's from 1961 to 2016. And you can see that a lot of the observations, they're concentrated around the stations, which makes sense.
So did you make this plot based on graphs?
Yeah.
And then can you use a raster field or something?
Can I use what?
Raster field or cell field or something. So this is, you just use a default setting, right?
Right.
So
yeah.
it's kind of linear interpolation. But the raster field or cell field is just only one cell box and then fill one color.
You put
Oh.
set GX out grid fill,
Yeah.
GR fill.
GR field,
G-
something,
oh,
yeah, something.
okay.
So you change that one. This is more
It's like tiles?
one, yeah, kind of
Yeah.
tile, and then
Or-
one number.
It
so
just
one
shows
color.
you only the grid box
Yeah.
Yeah.
value.
So that one is more better way to show this kind of
Yeah.
stuff. Okay.
Okay, grid fill.
Set GX out,
GR
GR
field
fill.
or something.
Mhm.
Yeah.
Okay, it's good to know. It's good to know.
So we more looks like a scientific.
Yeah, yeah, it's true. And the plot on the right is simply to show the number of observations since since 1891 to 2016, and I think
That's
we looked
crazy.
at this. Yeah, it's kind of odd because the number of observations really declines after 1980. So it should be the other way around, because with technology you should have more observations, but I think maybe that's more of an internal thing. I don't know why.
Does that have any potential implications for trends you've drawn since, you know, the 60s or 70s?
I mean, it could,
Yeah.
because that's a very steep drop.
Yeah.
Yeah,
That's crazy.
yeah. And this is just to compare the different data sets. So this is for the March to May time period, because that's when East Africa experiences long rains, and it's the long rains it's that season where rains are really, really declining. So this is simply to kind of verify that and compare GPCC data with other precipitation data sets.
Mm.
Yeah, and so GPCP and CMAP, they include satellite data, so it's just to see what the difference would be if you had additional data, what kind of trend you would see. So I mean, the fact that it's still declining in the plots here, it's something worthy of mention. Okay. That's it. Everybody? Okay.
Yeah, it's a good try. Yeah, I like that one. Okay.
Okay.
I'm nothing.
Nice.
So yeah, just finish.
Finish.
Bye.
Bye, Simon.
Bye, Simon.
Bye, Simon.
Have a nice
Say
day.
hello.